Now for this presentation, we are going to discuss on how we are going to find the domain of a function defined by an equation. So first is that how are we going to define what is the domain of a function? So the domain is defined as the set of input values for which the function produces an output value. So in other words, the domain is the full set of the x values that can be plugged into a function to produce a y value. So this is not new to us, class, because most often than not, when we input a value of x into a certain equation or a function in that matter, then we simplify the given functions where the value of x is given, then the result will be the value of your y. So how are we going to find the domain of a variety of functions? So these are the common type of functions, and depends on what type of functions will determine the best method for finding a domain. So I will be only presenting to you three common functions. We have the polynomial functions. So this is commonly seen in any algebraic expressions or any algebraic equations that we are going to solve for the variable y. Then we also have the rational function. So this is where there are two functions. One is in the numerator, the other one is in the denominator. And the radical function. So in this case, we have the square root of a given function, or sometimes we are given the third root, the fourth root, and so forth and so on. So first is that how are we going now to find out what will be the value of the domain of the given functions, given a functions in this matter. So we always assume, class, that the domain is the set of all real numbers, meaning the value could be a whole number, a negative number, a fractions, a decimal number. However, if the result class is non-real numbers, like an imaginary number, so that is already out of our discussion. So we only assume, class, that when you input a certain value of your x as an input value, so it could be any of this. So it could be a counting number, a whole number or zero, a negative counting number or a positive counting number, including fractions or irrational numbers like the square root of 2, the value of pi into the functions, then we are sure that the result should be also a real numbers. Otherwise, if the result is not a real number, then that would be now the exception to the rules. In other words, you're going to find those values that makes the result not real numbers. So for first type of a function, class, so this is the first rule. If you are given a polynomial function without radicals or variables in the denominator, so when we simplified, because sometimes, class, you are given a polynomial thinking that it is a radical polynomial or a radical functions, then once you simplified, we found out that it is simply a polynomial functions or a polynomial functions in this matter. So for this type of a function, the domain is all real numbers. So we don't need to show or find a value of your x to make it undefined or not a real number. So examples of polynomials, we have here a quadratic polynomial. So 3x squared minus 2x plus 1. We have a fourth degree polynomial, or we call it now a quartic. This is x raised to 4 minus 2x plus x minus 4. We have a 6th degree polynomial, 2x raised to 6 minus 2. Then another quadratic polynomial, negative x squared minus x plus 2. Then we also have another quartic. Now you notice here, class, that the exponents of your variable x are all positive, or if it is linear, then it is simply raised to 1. So if you encounter this kind of a function, we call this a polynomial functions, then what will be the domain? So the domain here, class, will be all real numbers. In other words, any real number, if you're going to substitute it into the variable x, then there is always a value for your f of x, which is also a real number. Now, the second rule is, what if we have a denominator that contains a function? So this function with a variable in the denominator, we call this now irrational functions. Now, if you encounter this kind of a function class, to find the domain for this type of a function, first, we are going to set the bottom equals to 0. Then we exclude the x value class you find out when you solve for that equation. So in other words, all you have to do, class, is look at the function in the denominator. Then we are going to equate the functions in the denominator to 0. Then we solve for the value of your x, and that value of your x is the one that we are not going to include. So we have to exclude that. So typically, we use the word except the value of your x. So how do we find for this exception? So this only applies, class, if we have a denominator, which is a function. So first, we take the denominator of 3x minus 9 and we equate this to 0. So we have here 3x minus 9 equals to 0. Then we solve for x. So we transpose negative 9 to the other side to become positive 9. Then we divide both sides of the equations by 3. Then your x is equals to 3. This means, class, that this will not be part of the domain. Because if you're going to substitute the value of your x to be 3 in this function, you will arrive at division by 0, which is not possible. So you cannot divide a number by 0, class, because it will make undefined. So with this exception, then we could say now that the domain will be all the real numbers except x is equals to 3. So in graph, class, this is how it looks like. So we have all the values of your x to be a real number, to a negative infinity, to a positive infinity, except that your x is equals to 0. You might be asking, sir, is it okay if the value of your x is 2.99? Yes, it will be a, there will be a domain, there will be a range value for that one. So if the value of your x is 2.99, there will always be an f of x equivalent. If the value of your x is 3.01, again, it still satisfies that there will be a value for your f of x, but not equals to 3, because it makes your denominator equals to 0. So if that happens, so we cannot divide a number by 0. Now let's have another example here. So again, our concern here, class, is your denominator. So we have x squared minus 16 as the denominator. So this is a uh, degree 2 function. So meaning there will be two values for your x. So we need to use our idea, class, for factoring. And this is actually the difference of two squares whose factors will be of the form x plus a times x minus a. So we are going to equate this into 0. Then we are going to solve for your x. So x squared minus 16 equals to 0. So you can transpose negative 16 on the other side. Now, to remove the exponent 2, so we need to take the square root of both sides of the equation. So taking the square root, what we will have is plus and minus. Okay, we always have the positive and the negative square root of 16. So that the square root of x squared is x, and the square root of 16 preceded by plus and minus will give us positive and negative 4. So there will be two values for your x that will not be part of the domain. So in other words, these two values of negative and positive 4 will make your denominator equals to 0, and you cannot divide a number by 0. So therefore, the domain will still be all real numbers except x is equals to negative 4 or x is equals to positive 4. So any value, class, will satisfy this function as long as the value of your x should not be equals to -4 or +4. Otherwise, it will make the function undefined. Okay, so what if we have another one? So we have this function 3x plus 4 all over 2x plus 12. So our concern class is our denominator. So again, we need to equate the denominator to 0. Then we solve for our x. So 12 will be transposed to the other side. It is -12. Then we divide both sides of the equation by 2. So the value of your x will be -6. So 2x divided by 2 is x. -12 divided by 2 is -6. Again, what will be the domain of these functions? It will be all real numbers except your x to be -6. So, kahit anong value class ng value ng x natin as long as it's real number except -6 will satisfy this function. So, all real numbers except x is equals to -6 will be the domain. And of course, if you are going now to represent this by a graph, so we have the real numbers here. So to negative infinity, to positive infinity, except that your x is equals to -6. So you notice, class, that we have an open circle indicating that -6 is not part of the domain. Okay, now the third rule is what if we have a radical symbol like square root, cube root, fourth root, fifth root. So this is where the rule number 3 will be applied. So a function with a variable inside a radical sign with an even index. So like for example, the square root of a function, the fourth root of a function, the sixth root of a function. So as long as the indices class is an even number or an even index, then this is the rule. To find the domain for this type of a function, so we simply set the terms inside the radical sign to greater than or equals to 0. So this is an inequality because we are going to include the 0 as part of the solution. So, and we are going to solve to find the values that would work for x, meaning whatever value for x that we solve, that will be the domain. So if we have a radicals whose indices are odd numbers like cube root of a function, okay, the seventh root of a function, or the ninth root of a function, or the fifth root of a function. So if this will be the case, class, then the rule is we don't have to solve for the value of your x to find for the domain. All we do, we just conclude that the domain is all real numbers, similar to the polynomial function. So our concern, class, is only if the index is an even number, like square root. So for the examples, class, so we will only use square root for this matter. So we have here the cube root of the 2x minus 1, the fifth root of x minus 5, the seventh root of 3x plus 1 half. Now, because their indices, class, are odd numbered, so they are not even numbered, so we don't need to solve for the value of your x. So automatically, we can say that the domain will be all real numbers. So any number that you're going to substitute here, then you take now the cube root or the fifth root or the seventh root, there is always the value of your f of x or the range value. Okay, so what if we have this? So this is a square root. So when the index is not indicated, class, so it means it is square root. So this is actually the reverse operation of the square. So the square root of 4x minus 10. So according to the rule, we are going to equate 4x minus 10 greater than or equals to 0, then solve for the variable x. So we equate this radicand to greater than or equals to 0. solve for x. So what we do is similar to the equations. So if negative 10 will be transposed to the other side, it becomes positive 10. Then if we divide both sides of the inequalities by 4, then 4x divided by 4 is x, then greater than or equals 10 divided by 4, or this is the same as 2.5, or 5 all over 2. So therefore, x is greater than or equals to 2.5. What do we mean by this one, class? So any value of your x, as long as the value of your x is from 2.5 and above, then that will be the domain of this function. Any value that is less than 2.5 will make this undefined. So it will only be 2.5 and above. So how are we going to state our domain? Then we could say that the domain will be all real numbers greater than or equals to 2.5. So in graph, we have here a closed circle indicating that from 2.5 and above up to positive infinity will be the domain for this particular function. Any value that is less than 2.5 will make this function undefined. Okay, so what else? Now we have another one. So we have f of x is equals to the square root of 4 plus 6x. So again, we are going to equate 4 plus 6x to not equate, but of course greater than or equals to 0, using now the inequalities, then solve for x. So 4 plus 6x is greater than or equals to 0. Then if you're going to transpose positive 4 to the other side, it becomes negative 4. But still, we have the greater than or equals to. So similar to the equations, if you're going to divide both sides of the inequalities by 6, and if you're going to simplify it, then 6x divided by 6 is x greater than or equals to negative 4 divided by 6 is negative 4 all over 6. Or you can simplify this further as negative 2/3. This is the same as negative 0.66666 in decimal number. So it would be more accurate, class, if you're going to use the fraction rather than the decimal number. So this is an example of a repeating non-terminating decimal number, the 2/3 value. So what will be our domain? So again, the domain tells us the result of your x, which is greater than or equals to negative 2/3. So any value that is greater than or equals to negative 2/3 will satisfy these functions. So those are the values of your x, or the domain. So we could say now that all real numbers greater than or equals to negative 2/3 will be the domain for this function. Or in graph, we can have this one. So again, the negative 2/3 has this uh, closed circle. So this is with a shading part, indicating, class, that negative 2/3 is part of the solution, or part of the domain. Okay. Now, sometimes, class, we have this kind of a function wherein when we equate this, or in inequalities greater than or equals to 0, there will be some changes of the inequalities. So similar to the two previous examples, we are going to equate 7 minus 4x greater than or equals to 0. So we have here now. Then we are going to solve for your x. So you have two options here, class. Either you are going to transpose negative 4x on the other side to become positive, or you are going to transpose 7 to the other side to make it negative 7. So we have two options here. So these two are the same. So if I'm going to transpose negative 4x on the other side, it becomes positive 4x. But if I'm going to transpose positive 7, retaining the negative 4x on the left side, then on the right side, the 7 becomes negative 7. Then if you're going to isolate the variable x, so here on the first one, I need to divide this by 4. But on the other side, on the other one here, I need to divide it by negative 4. So, yun lang pagkakaiba na class. So, if this happens now, so for the first one, dividing both sides of the inequalities by 4, so we have 7 all over 4 is greater than or equals to x. Now, in the second one, dividing both sides or multiplying both sides by negative, the rule will change. If you, again, in inequalities, if you're going to multiply or divide, okay, any side by a negative number, then the inequality will change to its reverse. So from greater than to, or greater than or equals to, because we divide this by a negative 4, then it becomes less than or equals to. So that's the rule, class. So here, on the first one, 7 all over 4 is greater than or equals to x. On the other one, x is less than or equals to 7 all over 4. These two class are identical. But if you're going to read the first one from right to left, so x is less than or greater, x is less than or equals to 7 all over 4, which is the same with this one. Okay, so when both sides are multiplied or divided by a negative number, the inequality symbol is reversed. So this one, by the property of, uh, let's say, mirror, or what we call now the, there's a property for inequality where you can uh, change now this one. So your x here will be on the left side, then it becomes now the less than or equals to. So they are now the same. So just be careful, class, when you divide an inequalities or you multiply an inequalities by a negative number, automatically you have to change the inequality in its reverse. Okay, so that's the rule, class. So what will be the domain? So the domain for these functions will be, again, all real numbers as long as it is less than or equals to 7 all over 4. So that will be the domain, class. Or in our graph, so starting from 7 all over 4 to the left, to the negative infinity. So we cannot list all the possible values of your x, but we just use this statement. So as long as they are values that is 7 all over 4 or less, then it makes this function work properly, or there will always be a value for the range. Okay, so that will be the domain, class. Ayan. Now, sometimes, class, we are given combinations of the rules, especially rule number 2 and rule number 3. Now, remember that for rule number 2, we have the functions in the denominator, and that will be the exception. For rule number 3, we are going to find that value of your x that will make, okay, the value of your x work for that functions. In other words, we are solving for the x that will identify the given domains. But if it is found in the denominator, that's rule number 2, then that will be the exception. So how are we going to solve for this one? So this involves a radical, which is rule number 3, and a denominator, which will be rule number 2. So you can solve for the numerator to find the value of your x that will make the domains. Then you can also use the rule number 2 for the denominator to identify which of the value of your x will not be part of the domain. So that will be our solution, class. So if I'm going to use first rule number 2 in the denominator, I'm going to equate x minus 3 to 0 so that I can solve for x. So this is easy. So x minus 3 equals to 0, so x is equals to 3. So meaning, as of now, the domain will be all real numbers except 3. Okay, so that will be our initial solution. But because we have this radical inside, then we can further identify which of those real numbers will be part of the domain only. But we now know that except x equals to 3, hindi siya pwede. So we need to further find out the values of your x, okay, under the radicand, to identify further what are the possible domains only. So far, using rule number 2, this means that the domain is a real number except 3, okay, for the moment. So if we apply rule number 3, we get the radicand, equate this to greater than or equals to 0, then solve for x. So if we do this, so 3 minus x is greater than or equals to 0. So if I'm going now to transpose negative x on the other side, so 3 is greater than x. So this is the same as x is less than or equals to 3. So in other words, class, the domain supposedly will be any value of your x as long as it is less than or equals to 3. However, there is an exception that x should not be part of the domain. So nagkakaroon tayo dito class ng conflict. So if we are going now to make a statement here to find for the domain, okay, then this is what it looks like. All real numbers less than or equals to 3 except 3. So, meron tayo dito equals to 3 except 3. So, to refine this statement, because based on rule number 3, 3 is part of the domain. But based on rule number 2, except 3 naman. So, we remove the values of your x to be part of the domain. And therefore, by refining this statement, then our domain will be all real numbers less than 3. And that will be the solution class. So we can have an open circle here indicating that 3 will not be part of the domain anymore. But any number as long as it is less than 3 will be part of the domain. Okay, so what if we do the reverse? Now this time, your radical is in the denominator. So this is, again, a combination of rule number 2 and rule number 3. For rule number 2, what makes the denominator equals to 0, that is now the exception. For rule number 3, what will be the value of your x will satisfy this inequality so that it will be the solution. Okay, so how are we going to do this? So we want the denominator not equals to 0 or negative because of the radical. So if you're going to take the square root of 0, of course, the result is 0. Then dividing any number by 0 is not possible. Or if the value of your denominator is negative, so what is the square root of a negative number? So it is already undefined. So those are the things that we are going to find out. Okay, so thus we equate the radicand in the denominator to greater than 0 only. So we do not include any more 0 here because when the denominator is 0, it makes the function undefined. So we remove the equality here. So we only deals with greater than 0. So as long as the value of your x is positive, then the function will work, and that will be the domain. So without the equal sign, we have to solve for x that will be part of the domain. So x minus 4 is greater than 0, then x is greater than 4. So any number, as long as it's greater than 4, will be the domain here. So your denominator will not be equals to 0 anymore. So just to find out whether... Okay, class. So if we are going to check this one, say for example, find for value for your x as long as it's greater than 4, then let's evaluate whether or not the result will not be divisible by 0, or it will not, or it will make our function undefined. So say for example, if the value of your x is positive 5, which is greater than 4, so substituting that into the function, and what we have is a value that is positive 11, meaning when the input is positive 4, then the output is positive 11. So any value that is greater than 4 will satisfy this function. Another one is if x is equals to 6. So substituting the value of your x to be 6 into the function, then you are going to simplify it. Then we have 13 all over the square root of 2. So when you divide 13 by the square root of 2, again, the result is an irrational number, which is a real number that is a positive number. And again, if we have inputted the value of your x to be 6, then there is the corresponding output value, which is also a real number. So meaning, if the value of your x, as long as it's greater than 4, then there is always the corresponding value of your f of x. Sir, what if the value of x is 4.01? Will the functions give us 0 as a divisor? No. Because if it's like, say, for example, 4.1, then 4.1 minus 4 is zero point 0.1. And square root of zero point 0.1 is not 0. So again, we still have a result. Now, what if we have x equals now to 8? So again, substitute the value of your x to be 8 into the function, then simplify, then what we have will be 17 all over square root of 4, which is now 2, then that would be still a real number. So as long as the value of your x class is greater than 4, then it will satisfy this function. So the domain, therefore, will be all real numbers greater than 4. Okay, so this will be how the graph looks like. So we still have an open circle here, meaning that 4 will not be part of the domain, but it could be greater than 4, 4.01, 4.001, as long as it is not equals to 4. If the value of your x is 0, definitely because 0 class is less than 4, so this will not be possible because 0 minus 4 is negative 4 and the square root of negative 4 is undefined. In other words, it is an imaginary number. The result is plus n minus 2i, which is an imaginary number class. So any number that is less than 4 is not possible or even equals to 4. So another example is this one. So this is a radical where the radicand is raised to 2. So we have here a degree 2 polynomial. So when we say degree 2 polynomials class, so there will be two possible values for your x. So if this happens class, so we really need to divide our values or range of values of your x, and we are going to find out which of those parts of your x will satisfy these functions. Okay, so first we are going to equate x squared minus x minus 6 greater than or equals to 0, then solve for your x. Now this is factorable, whose factors is x minus 3 and x plus 2 greater than or equals to 0. Now, similar to the zero product property, that each factor will be equated to 0. But in this case, we are using inequalities. So in other words, I will be equating x minus 3 greater than or equals to 0, then solve for x. Then I could also equate x plus 2 greater than or equals to 0, then solve for x as well. So we will be having two values for your x. So this will be our solution. So when x minus 3 is greater than 0, then x is greater than or equals to positive 3. But when x plus 2 is greater than 0, then x is greater than or equals to negative 2. So these two make no sense to us because if this is a solution that the domain should be greater than or equals to 3, then another one will tell us that x should be greater than or equals to negative 2. So how is these two are being, uh, let's say, we are going to find out which of these two will be really the solution. So what we're going to do here, class, is we are going to divide our number line system by identifying where is the negative 2 and where is the positive 3. So what we do is there will be values class that will be less than negative 2 there will be values between -2 and +3. Then there will be values greater than +3. Now, if the value of your x is -2 or +3, because we have here also equality, of course, it will be part of the solution. But what about those values that are less than -2, greater than +3, or values that is between -2 and +3? So we have to test this one. So you just choose a number less than -2, choose a number that is between -2 and +3, then choose a number that is greater than +3. Now, if I were you, class, so just choose a number that is close to -2, which is a whole number. It could be -3 or -4. Then a number that is between -2 and 3, then the easiest number is 0. Then a number that is greater than 3, then choose +4. Okay, you can choose also +5. Okay. For easier computation, class, that's the purpose. Now, let's say, for example, that I will choose x to be -3, which is greater than -2. Then between -2 and +3, I will be choosing 0. And any number that is greater than +3, I will be choosing 4. So I will be substituting this into this function. Now, remember, class, this is the factored form of the original function. So they are the same. So I will be substituting these three values that I chose. Then simplify. So I have here x minus 3. So -3 minus 3 times -3 plus 2 greater than or equals to 0. Then here I also have 0 minus 3 times 0 plus 2. So I am using this factored form function. Then for x equals to 4, I have 4 minus 3 times 4 plus 2 greater than equals to 0. Then simplifying, so -3 minus 3 is -6. -2 plus 2 is -1, greater than or equals to 0. Here we have -3. 0 minus 3 is -3. 0 plus 2 is +2, is greater than or equals to 0. Then here we have 4 minus 3, that is 1, and 4 plus 2 is 6, greater than or equals to 0. Then simplifying further, so -6 times -1 is +6, is greater than 0, which is true. So 6 is greater than or equals to 0. So it's a true statement. Here, -3 times +2 is -6, is greater than or equals to 0, is a false statement. So this is not true. And 1 times 6 is +6. So 6 is greater than or equals to 0. Again, this is also true. So this means, class, that when the value of your x is less than -3 or -2, and the value of your x is greater than +3, then it makes the function correct. But any value that is between -2 and +3, it will make the functions not true or a false function. So we can now see clearly what will be the domain because of this result. So therefore, if we have any value that is less than -2, because it is true, then it is part of the domain. However, any value that is between -2 and +3, it is a false statement. So this number, any number between -2 and +3, will not be part of the domain. While any number that is greater than 3 will be part of the domain. So therefore, our domain will be all real numbers except numbers between -3 and -2 and +3. Or you could say that the domain are all real numbers less than or equals to -2 and numbers greater than or equals to +3. So this will be the case, class, when you have a function that is degree 2, which is under a radical sign. Then you will be going to test the possibilities, class. But if your radicand is simply a linear function, then we just simply equate that to greater than or equals to 0, and that will be the domain of your radical functions. So again, going back to rule number 1, so if a polynomial function is given without any radicals or variables in the denominator when simplified, then the domain is all real numbers. But if a function has a fraction, okay, or with a variable in the denominator, then to find the domain of this type of a function, so we set the denominator equals to 0, then solve for that x value, and that will be excluded in the domain. So that will not be part of the domain. For rule number 3, if a function with a variable is inside the radical sign, especially if it is a square root, now to find for the domain of this type of a function, we simply set the radicand inside, or the terms inside the radical greater than or equals to 0, then we can solve for the value of your x, and that would be the domain of the function. Otherwise, if the function has a radical, okay, with an even index, so you could just exclude any numbers for which the expression inside the radical is a negative number. Okay, so that will be our rule class for these three common functions. And that's it. So thank you for your time and hope to see you again, class, for the next lesson. Bye bye, everyone.